Go. All right, so this is now 5-4. Okay, the video shall be called 5-4. The notes shall be called 5-4. Okay, we are now on 5-4. So how a muscle contracts. So what we can see is that a muscle right here needs to contract in order to pull on the bone. So the muscle, it reaches down and grabs onto the part of the bone that it's going to pull upwards. Do you guys remember what this part is called right here? The insertion. So what's this part up here? Origin. Okay. So the insertion is always on the movable bone, which causes the bone to come up, which causes the muscle to contract, causes all these old lines to get closer together. So that's what we're going to be talking about today, is how do I get my thought from here to go down here, and into my muscle. All right, so this is, like I said, this is kind of review. So we talked about this stuff yesterday, so it should just be kind of review for you. So we said that muscles begin, excuse me, with a the muscle contraction begins with a current. And so we talked about electricity being able to be passed through, just like electricity would go into a plug and go into your phone when you're charging it. So that flow of electricity we refer to as an action potential. So the action potential is just fancy vocab for flow of electricity. Then we said that we've got the excitation-contraction coupling, which is just a series of events that link the electrical signal as it travels down the nerve and into your muscle, causing your muscle to contract. So all the events that occur, now this is just a spinal cord here, it would go up to the brain. So all the events that are telling your brain to tell your spinal cord to tell your nerve to tell your muscle to contract is referred to as the excitation-contraction coupling. Okay, we said that we've got motor neurons. You have a couple of different kinds of neurons. Actually, let me go back to that picture to explain. You've got sensory neurons. See this guy when he smacks your knee? You pick it up in your senses, and it travels up and goes to your spinal cord or up to your brain. We only care right now about motor neurons, which are the ones that go away from your brain and spinal cord and attach to the muscle. So you have sensory neurons, motor neurons, and these weird things called interneurons. We only care right now about the motor neurons. So the motor neurons are nerves of the somatic nervous system. Somatic means that's under your voluntary control. See, this is what happens to my pen. For some odd reason, when I'm recording, it starts, like, doesn't flow even. I don't know why. So the motor neurons are the ones that go from the brain to the spinal cord to the muscle themselves. And then we talked about the structure of a nerve itself. That is kind of very similar to the structure of a muscle. That you have an axon instead of a myofibril, and you put a whole bunch of axons together and you get a bundle, kind of like a fascicle. And then when you put a whole bunch of fascicles together, you get the actual nerve itself, kind of like the full muscle. And so when you look at a cross-section of a nerve, man, you can see all these little nerves in here, and you can even see some blood vessels, because even nerves need a constant supply of oxygen and food. And so all nerves will have a blood supply in it. It's kind of like when we looked at the cat thigh muscle. It had that, remember there was like a big vein that separated the two? Well, there was a vein and a nerve that was right next to each other in the inside of the cat thigh. Now a neuron, when we look at a neuron right here, make it a little bit bigger, like that. When we look at the neuron, we see that it has the main portion called the body. We've got these little branchy things that stick out called dendrites. And we have this long section right here called the axon. And the axon is the main thing here. They're the main ones that are doing the job. Because information, the electrical current or the action potential flows in through the dendrites, through the axon, and pops out the other side. And that's what we're looking at. When we look at the charges trading places, we're looking at all that's going on here in an axon, and we're also looking at what's going on here at the head. Because at the end of the axon, that's where it attaches to the muscle and all this good stuff starts. Okay, so we've got an axon, comes down like this, and then the axon head or axon terminal or axon terminus is the end of the axon, where it embeds itself into the muscle fiber. So if we carry this out, this is just one section of a long fiber. And we can see our little sarcolemma inside. There's a myosin, and the blue, there's the actin. So each sarcomere has its own little tube right here, which we identified before as being a T-tube. And the axon doesn't directly touch the sarcolemma, but creates this little area. Now the whole area together we call the neuromuscular junction. Neuro for the neuron, muscular for the muscle. So it's where they attach, but they don't touch. That space in between where they don't touch is called the synaptic cleft. So all this space in here is called the synaptic cleft, and that's where the business end of the axon and the muscle tend to do their job. The synaptic vesicles are little bubbles inside of the axon who carry something called a neurotransmitter. A neurotransmitter is just a chemical that has the ability to pass on a message. So like that game you used to play as a kid where you would telephone, you know, you'd say one thing to another, but then by the time it came back it was horribly misconstrued. Well, thankfully acetylcholine doesn't do that. These neurotransmitters will keep the message the same, but they pass the messages. So the synaptic vesicles contain ACH, or the fancy word acetylcholine, and what they do is that they carry the messages across to the other side. So the area where they send the messages to is called the motor end plate. The motor end plate is this little highly folded area right here where all the receptors are. There are acetylcholine receptors that dot the lining of the motor end plate like this. Now we know that anytime there's folds in something, you get greater surface area. Greater surface area means more receptors. Okay, so the folds provide large surface area for the receptors. When an impulse, which is the electrical signal, reaches the end of the axon, so this is an axon right here, when it reaches the end, it causes these little gates to open. There's gates all over the outside of the axon, causes them to open, and that allows calcium ions to flow in. When we get enough calcium flowing in, that causes these vesicles to migrate down to the end of the axon and then spill their guts into the synaptic cleft. Now in here we have little triangles that are representing acetylcholine. So once they barf out the acetylcholine, it hops across to the other side, carrying the message to the receptors. And here you can see the receptors fit the acetylcholine perfectly. And so once they fit inside of there, that will continue carrying that message on down to the next neuron, or in our case, to the next muscle. But if acetylcholine stays there, it will continue telling your muscle to contract, and we don't want that because that's where you get funky toe cramps. So how do we get this to stop? Well, there's an enzyme you can see right down here called acetylcholine esterase. Okay, big word, but if you break it down into its bits and pieces, it's not too bad. So we got the acetylcholine, and then the ester and the ace. So this enzyme right here will grab onto the acetylcholine and break it down into its two components. Acetic acid, the main component of vinegar, and a structure called choline. The acetic acid and the choline will then go back into the axon and get reformed back into the little triangles of acetylcholine to just do this over and over again. So all they do is go back and forth and back and forth. So if we don't break down the acetylcholine, that's when we get a toe cramp or a calf cramp or something like that. Okay, once the information gets into the sarcolemma, because remember we got our muscle fiber here, so once the axon tells the sarcolemma that, hey, it's time to contract, then here's what's going to happen in the sarcolemma. You have pumps. You have a sodium-potassium pump. You have just a potassium pump and a sodium pump. Okay, so these are the three main players. So if you notice, I picked a new picture for some of this stuff to help explain it better. So we've got these 3 pumps which are located in the lining or the membrane of the sarcolemma. So this is the sarcolemma, which is just another name for what? The cell membrane of of the muscle fiber. Sarcoplasm is the cytoplasm inside, down in here. So we have our sarcolemma, which has all these pumps in it. And what happens is that as my electrical current comes by, you can see there's little positive charges on the outside and negative charges on the inside. And that's just because the sodium on the outside, there's more of those out there than potassium's on the inside. So that makes this area slightly positive and the potassium slightly negative comparatively. It's not that potassium is negative, it's just that it's more negative compared to all that sodium out there. So what happens is when the positives and the negatives, when they trade places going through the potassium channels and such, then that causes just as a wave. I think we talked about the wave, doing the wave in a big stadium. So that's exactly what happens, is that these little guys open and they trade places. The potassium goes out, so the potassium goes out here, and the sodium goes in. That causes a momentarily change or flip of charges. But as soon as you stand up and do the wave, you sit back down again. And that's where this pump comes in handy. It shoves everybody back to their normal side. Okay, so there's 3 main steps how that happens. First step is the depolarization and generation of the action potential. So here's the axon, but it also works for the sarcolemma as well. Sarcolemma. It works the same. So the action potential, doing the wave, works its way down when sodium goes in and potassium comes out. That's the standing up portion of the wave. And just as soon as that happens, potassium gets pumped back in, sodium gets pumped back out. But the fact that they flip places tells the next guy in front, kind of like doing the wave. If I do it, the guy next to me better get up and do it too, right? So when these guys flip places, they tell the guy next to him to flip as well. That leads to the second step, which is the continuation of the wave. So if I get up, then the guy next to me gets up and sits down, the guy next to him gets up and sits down, and this just keeps on going, traveling down the length of the whole entire fiber. So the sarcolemma just keeps flipping. Positive goes in, negative goes out, and then it flips back right afterwards. The third step then is going to be repolarization. This is where the sodium-potassium pump comes in handy, because what he does is he restores everything back to normal. That's sitting back down. So I found this picture here that kind of explains it really well. So here's the action potential, the flow of energy, and what you can see is that the sodium went in, the potassium went out, and that caused the negative to be outside and the positive to be inside. Then it keeps on going. You can see it flowing down in this direction, but look what happens. The positive goes back to the outside, the negative goes back to the inside. This keeps on going until you hit the end of the cell. Once you hit the end of the muscle fiber, it just stops. Now what we're going to be learning next is that if this is a muscle fiber, what are these little areas right here? So here's a Z line, and it goes in like this. We've got the myosin like this. Here's another Z line, goes like that. What is this? Do you remember the name of that? Refers to the word transverse. T? Tubule. So what happens is as this flipping of charges works its way down the sarcolemma, it's going to take a dive into the T-tubule. Once it goes into the action potential, goes into the T-tubule, then it's going to spread out over the sarcolemma, and that's what's going to cause the actual contraction. So that's what's next, is the actual physical moving of the actin and myosin causing your muscle to contract. So all of this just was to get the thought from your brain down to the muscle. That's it. All of that, all 14 minutes of it, just to get the thought of moving your muscle down to the cell membrane, the sarcolemma of your muscle itself. All right? I do believe that is the end of that, so we shall call it quits for today. So once again, this is 5-4. All right, we're done. Everybody say goodbye.